So one thing one notices is that in the examples that I gave, all the pictures were sitting in first case in R2, second case R3. Here I did not assume that the set is sitting inside any Euclidean space at all. It's a purely abstract definition. But fortunately it turns out that there are these so-called embedding theorems which say that this abstractly defined object can actually be regarded as a subset of some Euclidean space. Regarded means that every n manifold, the technical term is, can be embedded in R2n plus 1. Embedded just means that there is a one-to-one onto mapping from M onto some subset of R2n plus 1 with continuous inverse. So for all practical purposes, we can think only of subsets. If you want to talk about manifolds, we can think only about subsets of Euclidean spaces. However, that's not in many situations, that's not the right way to do it. In fact, it's not very helpful to think of them as subsets of Euclidean space. Rather, the intrinsic property, namely that locally homeomorphic, that is the key thing, not the fact that it is sitting inside this. Okay, so then now just this manifold by itself is very difficult to work with, even though substantial work has been done for these topological manifolds. Rather, what one is interested in is, before I proceed, maybe I should mention one thing. One concrete, these objects, these manifolds occur all over mathematics, but not just in mathematics, even in physics. In fact, according to Einstein's relativity, according to Einstein's theory of general relativity, the universe, the technical term is space-time, is itself a manifold. So, the space in which we exist is a manifold. In particular, it means that it's not just a Euclidean space it may not be just Euclidean space. It may be something more complicated. It's hard to visualize this. Nevertheless, this is the standing assumption here. But it's not just a topological manifold. So far I've just talked about topological manifold. It is assumed to be what is called a smooth manifold. So that's the next object that I'll discuss. Now, how much time have I?
10 more minutes.
10 more minutes, okay. So as I said, these objects, topological manifolds, are important, but perhaps more widely occurring class of examples and things which do crop up in practice are the smooth manifolds. So the idea is simple. On a topological space, we can talk about continuous functions, but we would also like to talk about smooth functions, differentiability of functions, taking derivatives and so on, doing calculus. So how is it possible to define a notion of a smooth function? How do we define a notion of a smooth function? Usually one talks about the domain of a smooth function is an open set in Rn. So this is the usual setting for calculus, multivariable calculus. You have an open set in Rn and then you have a function from here to R. Then one can talk about its partial derivatives or total derivative, directional derivatives and so on. At any rate, one needs an open set. Now it's tempting to see if this can be used to define a smooth function on a topological manifold. Let's do that. So let M be a topological manifold, be a topological N manifold. We know what it means for a function to be smooth on an open set in Rn. That's the standing assumption here. So with that, let's see if we can define a smooth function on this object. So let f from M to R be a function. Now by definition we know that every point here is locally like the unit ball. So let's take a point on the manifold. We know that there is some set, open set V, and a homeomorphism phi into the n-dimensional ball. On the other hand, we already have a function defined on the whole space here, f. Now this open set is the same as this Bn, same in the sense of being homeomorphic. So what one can try to do is one can look at the inverse mapping here, which will take the n ball into this open set, then compose with f. One gets f composed with phi inverse is then a map from Bn to R. So we are back in the familiar setting of multivariable calculus. We have a function from an open set in Rn into R. Bn is an open set and we have this. So we can say that this function is smooth if this is smooth. Let us define f to be smooth if this is smooth. For now, the key point is for all such, there was a choice involved here. We started with a point, we took some v, and then for all such v and the corresponding phi. One immediately runs into a problem with this definition. The reason is, let's take the case of the two-dimensional sphere S2. This is a topological manifold, of course, and so I can take two open sets. One is this portion, the other one is the one hemisphere starting from, not exactly hemisphere, one which goes up like this. The point is that this piece, each piece, there are two pieces here, caps, each piece is homeomorphic to the two-dimensional disk, and every point is contained in one of the two. However, there are some points which are contained in both. So then what do we do? Well, according to this definition, let's say we take this point. For this I have a map phi onto the two-dimensional disk. Now for the lower half also I have another map C into the two-dimensional disk. The definition demands that both these should be smooth. If you look at it for some time, you'll quickly realize that there's no way this can happen. If you do a bit more stuff, and then if you use the fact that composition of smooth functions is smooth, you will be forced to the following conclusion. So this one has to check, but the conclusion is that, so this is for all such things. However, this definition is ambiguous. The ambiguity disappears if the following condition holds. It's precisely this, the ambiguity is precisely this, what I talked about. The fact that the single point can be contained in two different, these are called charts. Every time you have an open set homeomorphic to the ball, the open set along with that homeomorphism is called a chart. If a point is contained in two different charts, we are demanding smoothness of both of these, which may not happen unless whenever V alpha intersection V beta on T. So this is my, let's say, one V alpha, this is V beta. Then see, the thing is that this is the V alpha intersection V beta. This is the problematic region. If I pull it back here, I'll get something here. In this case, actually, you'll get something like this. C inverse V alpha intersection V beta. If I pull back this problematic part here, I'll get V alpha, C inverse V alpha intersection V beta. So whenever the intersection is non-empty, now this can be mapped here first and then here, this common region. So actually let's call it C beta inverse composed with V alpha. This will be a map from this open set to this open set in Euclidean space. And I can do the other way also. I can start here, come here. C beta composed with V alpha inverse are both smooth. in the usual multivariable calculus sense, since these are open sets. The domains of these two are open sets in Euclidean space. So this compatibility condition, it looks complicated, but unfortunately this is forced if one takes this point of view. So this is the definition of a smooth, that's it. A smooth manifold is a topological manifold with the property that whenever the two of the charts intersect, we have these are called transition maps. They are smooth. Now, the advantage of working with smooth manifolds are almost immediate. One has lots more tools to deal with, and one can get lots of examples very easily. One particularly useful way of getting examples of smooth manifolds is the following theorem. So let us start with our usual Euclidean space, and let's take a function, smooth function, from here to here. So let's look at the level set of a point, level set of a value, level set, which is set of all x which will map to a single point, f inverse q. So as a concrete example, if we take f of x equals x1 squared plus xn squared, the level set of any r greater than 0 is just the sphere of radius r. The level set of the point 0 is the point 0. The level set of some negative number is empty. Now, this theorem says that usually most of the cases level sets are actually manifolds. Then this is a manifold of dimension n-1 if q is a regular value, i.e. for all x in the level set, the derivative of f df. The derivative of f in this case is just a row vector consisting of the partial derivatives of f with respect to x1, etc. That derivative should not be the zero vector at the point x. And this should happen for every x in the inverse image. If this condition is satisfied, and this is quite easy to check. So, if this condition is satisfied, then one gets a manifold. Smooth N manifold. And level sets, I mean, one is constantly looking at level sets in physics or mathematics, even in economics. Whenever you have a function, it's natural to look at all those points which map to which assume this function is constant. So one gets lots of manifolds this way, and there are various other ways of getting smooth manifolds. And again, even in the smooth manifold category, one has this Whitney's embedding theorem. Every smooth N manifold can be smoothly embedded in R2n+1. So the from the topologist point of view, the next task at hand is, whenever we have mathematical objects, we would like to say when they are the same, equivalent to one another. For example, groups, we have the notion of isomorphism. Vector spaces, we have again invertible linear transformation, bijective linear transformation, and so on. In topology, the notion of homeomorphism is the right notion. Here, whenever you have two smooth manifolds, there is this notion of diffeomorphism, which is the homeomorphism between two manifolds, which is also smooth, and the inverse is also smooth. Now, I've only defined the notion of a smooth function. In other words, the target should be R. But it's not more difficult to define the notion of a smooth map between two manifolds. It's a slight generalization of what I defined. So, you have a notion of a smooth map. Then you say that a homeomorphism between two manifolds, if it is smooth and the inverse is also smooth, so these are two smooth manifolds, F a homeomorphism, if F and F inverse are smooth, then F is said to be a diffeomorphism. And this is the notion of equivalence. So, a topologist at this stage would be interested in understanding, say for example, if you start with the simplest case, one-dimensional manifolds. What are all the one-dimensional manifolds up to diffeomorphism? In other words, can we say that every one-dimensional manifold is diffeomorphic to either this or this or this, where you have a concrete list of examples? In one dimensions, it's quite straightforward. This is called the classification problem. Of course, this problem is there even in the earlier setting of topological manifolds. So one dimension. Can we say that every one-dimensional manifold is homeomorphic to something specific? If you think about it, in the first list of pictures that I drew, I had an interval, then I had a circle, then I had two circles and so on, and I had a square. Well, let's get rid of the two circles by saying this manifold is connected. M connected. Then I have an interval, a circle and a square. Square doesn't quite fit into the smooth manifold category, but let's take something else like a cartoon figure of an amoeba. So this, even though this looks very twisted, but this is just, one can check that this is diffeomorphic to the circle again. So one can't think of any examples, and in fact one can prove that every one manifold, smooth or non-topological, is diffeomorphic to an interval or a circle. Two dimensions onwards, it becomes more interesting. So I'll just end with this two-dimensional thing. Let me add in one extra word, something called orientable. Every orientable two-manifold is diffeomorphic to well, what are the examples I had drawn? The sphere, the ellipsoid, and again let's leave out the cube and a torus. But ellipsoid is the same, diffeomorphic to a sphere. So the list diffeomorphic to either a sphere or a torus or one of these. So what I'll do is I'll take a torus, I'll attach it to another torus like this, and I can keep on doing this. I get infinite number of examples. So a sphere, a torus, or one of these. This is a complete list of, here I have to add compact. Every compact orientable two-dimensional manifold is one of these. Three-dimension onwards it becomes very difficult. So three-dimension it leads to Poincaré's conjecture and so on. Okay.